So, namaskar, adab, sat shri akal, kaisa hai, 𝐂𝐤𝐬, hello and welcome in GATE Wallah. So, this is your next lecture of the subject vibration. Just one second. Na? Yes. So, this is your next lecture of the subject vibration. This subject we are discussing for aerospace engineering branch. What I am doing now, I am trying to complete one topic in one lecture. Okay. Like yesterday, we have completed that natural vibration of single degree of freedom system. Today, we'll discuss free damped vibration of single degree of freedom system. This is very important topic. Okay. So, today we are going to discuss free damped vibration of single degree of freedom system. So, first we'll discuss its introduction, that is what is free damped vibration. Then we'll discuss free damped vibration of general spring mass system. Okay. After that, we'll discuss free damped vibration of other cases. Other cases means cases which is other than general spring mass system. Okay. Yesterday when we were discussing natural vibration, in that discussion also first we had discussed natural vibration of general spring mass system. Then we had discussed natural vibration for other cases. Similarly, first we will discuss free damped vibration for general spring mass system. Then we will discuss these things for other cases of free damped vibration. So, I am discussing. First of all, what is free damped vibration? So, see, what is free vibration, that we already discussed in last class. Again, I am repeating. See, if during vibration no external time dependent force acts, then that vibration is known as free vibration. Listen carefully. If during vibration no external time dependent force acts, then that vibration is known as free vibration. Now, what about damped? See, if during vibration there is no resistance in vibration, okay, then that is undamped. But if there is resistance in vibration, resistance can be in the form of friction, it can be due to viscosity of the viscosity of the fluid. But if there is some resistance in the vibration, then that vibration is known as damped vibration. So, today we are going to cover free damped vibration. Free damped vibration means, first thing, during vibration no external time dependent force will act. But second, there will be some damping because it is damped vibration. Damping means, generally for damping we will attach in vibratory system, we will attach a device which is known as damper, and damper will provide damping, that is resistance in the vibration. Okay. So, if during vibration no external time dependent force acts and there is damping or resistance in vibration, then that vibration is known as free damped vibration. This is the simple general case of free damped vibration. What we have done here now, with this point mass we have attached a spring whose stiffness is K. Now, parallel to the spring we have attached a device which is known as damper, and whenever damper is present in the system, it will provide damping or resistance in the vibration. Okay. But it is free damped vibration. Why free damped vibration? Because to initiate the vibration, what I am doing, I am disturbing the mass by applying an impulse force from its mean position. Impulse force means we are applying this force for short duration. Now, suppose after disturbing the mass from its mean position, okay, by applying an impulse force, suppose I have disturbed till this point. After that, whatever force I have applied to disturb the mass, I have released that force. And if you release that force now, this system will vibrate like this, and this vibration will be free vibration, because whatever force I have applied to disturb the mass, now I have removed that force, means during vibration no external time dependent force will act, so it is free vibration. But since there is damper in the vibratory system, it will provide resistance. Resistance means, if there is no damper, means it will be natural vibration, and in case of natural vibration, what will happen? System will vibrate with constant amplitude. But if there is damper, so since damper is resisting the vibration, so if due to the in the presence of damper, if vibration will occur, then also the amplitude of that vibration will reduce with time. Reason? Because damper is resisting in the vibration. But how, that I will prove later. But right now this is the example of free damped vibration. So, I think it is clear to everyone. Okay, I had discussed the definition. During vibration no external time dependent force is acting, means it is free vibration. and since damper is present, it will provide resistance in the vibration. That's why it is free damped vibration. Okay, and it is general case of free damped vibration. General case means whenever a spring is directly connected to the point mass and parallel to the spring, if damper is attached, okay, then this is general case of free damped vibration. Okay, why I am discussing general case first? Because whatever final conclusion will come for general case, na, that will remember. And if you understood these things for general case, then you will be able to solve the problem of free damped vibration for other cases also. But for that, first I need to discuss general case. So now we are discussing free damped vibration of general case. In general case means a massless spring, suppose whose stiffness is K, is directly attached to the point mass M. Now parallel to the spring, one device is attached which is known as damper. This is damper. It will resist the vibration. Okay. Okay. In damper, one important parameters comes into picture which is known as damping coefficient. I will discuss its significance. Okay. But right now I am denoting damping coefficient as C. So what is C? Like K is the stiffness of the spring, na? M is the mass of this body. Similarly, what is C? C is the damping coefficient of the damper. What is the significance of this? That will come later, na? And right now we are assuming it is viscous damping. Okay. Now, first we will derive the governing equation. Okay. And whatever final governing equation will come for general case, that will remember in our mind. So to derive the governing equation, what I am doing, suppose we have disturbed the mass from its mean position, now it is vibrating. So I am taking any position in which this mass is disturbed from its mean position by x distance. It is displacement from mean position. Now if mass is displaced from its mean position by x distance, velocity will be x dot and acceleration will be x double dot. Okay, and since we are calculating x dot and x double dot by differentiation, direction of x dot and x double dot will be same as x. Okay. Now when we are deriving the equation of vibration, first conclude for restoration. Restoration means if a spring is present, definitely restoration will occur due to stiffness, there is no doubt. But first do analysis whether restoration will occur due to gravity or not. Because if restoration is not occurring due to gravity, during the derivation of equation of vibration will not consider the weight, neither will consider the static deflection of the spring due to weight. But if restoration is occurring due to gravity, then we will consider the weight also. That I discussed in last class also. See, here now you can see at mean position the weight of this body is supported by spring because weight is acting in this direction. So can I say here, it is true that weight is acting in the vertical direction, means in the direction of vibration. But due to weight, there will be some static deflection in the spring. And since due to weight, there is some static deflection in the spring, can I say they will counter each other effect because due to weight, there will be static deflection in the spring. And since they are cancelling each other effect, in this case, can I say there will be no role of gravity in the restoration. So in this case, there is no role of gravity in the restoration because due to weight, some static deflection will come in the spring, they will cancel each other effect. So here during derivation of vibration, neither will consider weight nor will consider static deflection of the spring because they will cancel each other effect, but how they are cancelling, don't bother about that. Okay. So now what I am doing, I am applying forces one by one. First I am applying restoring force. And here restoration is occurring only due to spring. And how we can calculate restoring force due to linear spring? Stiffness of this spring is K. Now see its displacement from mean position. See, the displacement of mass from mean position is x. And right now spring is directly connected to the point mass. So can I say the displacement of spring also from mean position is x. So here restoring force will be Kx. And in the body of mass, it will be opposite to x. Right now x is downward, so it will be upward. This is restoring force. Okay. Now here in free damped vibration, one more effect will come due to the presence of damper, which is known as damping force. Because here damping is providing the resistance. Okay. Now right now suppose I am denoting damping force as Fd. So how you can draw Fd? Then I will write the expression of Fd also. But first I am discussing how you can draw its direction. So see, damping force is provided by the damper. Suppose it is Fd. Now you can remember that this damping force will always be opposite to the motion because it is registering the motion. And generally now motion is described by velocity. Why? Because see, if I am going in this direction now, my velocity will always be in this direction. It might be possible my acceleration is in this direction, because if my velocity is decreasing, acceleration can be velocity opposite to velocity, but velocity will always be in the direction of motion. And since damper is resisting the vibration, it will be opposite to velocity. Means can I say it will be opposite to the since damper is resisting the motion, it will be opposite to the motion. Means can I say it will be opposite to the velocity? So see, damping force is always opposite to the velocity. Now displacement of mass from mean position is x, so its velocity is x dot. So can I say velocity of damper is also x dot, because it is directly connected to the mass. So damping force is opposite to x dot. Right now x dot is downward, so it will be upward. Right now I am denoting damping force as Fd. Okay, but what is the expression of Fd? So see, for viscous damping now, and right now it is viscous damping. See, damping force is always proportional to velocity. Okay, it is based on various assumptions. Various assumption means the fluid which we are using in viscous damping is Newtonian fluid. The gap of fluid is very less. So based on these assumptions, we are assuming, and in our BTech syllabus, this is by default assumption, that damping force is directly proportional to velocity. Right now velocity of damper is x dot, so it is proportional to x dot. Now whenever we'll remove proportional sign, one constant will comes. So here the constant I am denoting as C, and this C is known as the damping coefficient of the damper. Damping coefficient of damper. Okay, examiner will give the value of this C because it depends upon the damper. If we write its SI unit, SI unit of this will be C is nothing but Fd upon x dot. SI unit of Fd is Newton per. SI unit of velocity is meter per second. So it is Newton per meter per second, or you can say also it is Newton second per meter. Okay. So simply you can remember, like restoring force is K into X. It is opposite to X. Similarly, damping force is C into velocity, and it will be opposite to the velocity. If the velocity of damper is x dot, damping force is Cx dot, it is opposite to x dot. If the velocity of damper is, suppose in some other case, it is x1 dot, so damping force will be Cx1 dot, it will be opposite to x1 dot. So here, if damping coefficient of this damper is C, so you can directly write the expression of damping force. It will be C, the velocity of damper is x dot, so damping force will be Cx dot, its direction is opposite to x dot is downward, so it will be upward. So now we have applied damping force also. Now next, we need to apply pseudo or inertia force, because system is not in equilibrium. So to use equilibrium equation, first we will apply pseudo or inertia force. And this will apply for that body whose mass or inertia is given. So mass of this body is given, it is m. Now see, its acceleration is displacement from mean position is x, so acceleration will be x double dot. So pseudo force or inertia force will be mx double dot, and it will be opposite to x double dot. Right now x double dot is downward, so it will be upward. Yes. Okay. No other forces are coming, and since we have applied pseudo force, we can use the equation of equilibrium. So in this FBD, what I am doing, I am using summation of force in vertical direction or y direction and equating with 0. And while using this equation, suppose I am adding upward force and subtracting downward force. So right now mx double dot is acting upward, which I am adding, so plus mx double dot. Cx dot is also acting upward, which I am adding, so plus Cx dot. Kx is also acting upward, which I am adding, so plus Kx equal to 0. So it is the governing equation of general case of free damped vibration. This you can remember in your mind directly. In undamped vibration, this Ch dot part was not coming. Equation was mx dot plus Kx equal to 0. But in free damped vibration, in case of general case, this damping force, that is Ch dot, will also come in this equation. Okay. So you have to remember this equation. And in this equation, the coefficient of x double dot is m. For general case, coefficient of x dot is c and coefficient of x is k, where m is nothing but the mass of point mass, c is the damping coefficient of the damper, and k is the stiffness of the spring. But this is equation for general case. Okay. So this is very important equation. This will remember. Okay. Now, in free band vibration, how vibration will occur, or vibration is occurring or not, that how we'll come to know. For that, we need to find the solution of this equation. Solution of this equation means we need to find the solution of this equation means we need to find the x as a function of time, because in this equation dependent variable is x and independent variable is time. Now, finding the solution of this equation is purely mathematics, because it is double order linear differential equation and we want to find its solution. Okay, and here we are not going in too much mathematics. Okay, but some mathematics part I will explain because it is required for understanding, but I will not discuss complete derivation. Okay, complete derivation. But don't worry, you will not be face any difficulty in solving the questions. Okay, so see, whatever I am discussing right now, I am discussing just for understanding. Don't try to mug anything, just try to understand the things. At last I will make the summary and you have to only remember the summary. Summary is very simple, and if you have understood the summary and you remember the summary now, you will be able to solve the any questions of general case of free band vibration. Okay, so see, right now we got this equation. It is mx double dot plus cx dot plus kx equal to 0. Right now I'm not completely, but I am discussing some mathematics part. What I am doing now, I am dividing in this entire equation with m. So it will become x double dot plus c upon m x dot plus k upon m x equal to 0. Now can I say x double dot is nothing but d square x by dt square plus c upon m, x dot is nothing but dx by dt plus k by m x equal to 0. See, this is nothing but it is linear differential equation of second order with constant coefficient. Okay, this you will study in mathematics. Okay, why it is linear differential equation? See, if any differential equation, the power of differential coefficient is 1 and power of dependent variable is also 1. Like here, if you see power of this differential, it is double order differential coefficient, but its power is 1. Similarly, the power of this differential coefficient is also 1. Power of x is also 1. Okay, then that equation is known as linear differential equation, and since its highest order is 2, it is linear differential equation of second order. Now with constant coefficient means, coefficient means, if you see the coefficient of dependent variable, it is constant. Coefficient of this differential coefficient, it is also a constant. The coefficient of this differential coefficient, it is 1, which is also a constant. So if in linear differential equation, the coefficient of differential coefficient and dependent variable is constant, then that linear differential equation is known as linear differential equation with constant coefficient. Constant coefficient. Okay. Now in linear differential equation with constant coefficient, now some separate function of independent variable can come. Like right now, no separate function of independent variable is time here. So suppose here instead of 0, suppose 3t is coming. That is also linear differential equation with constant coefficient. But right now this separate function of independent variable is not coming. Means what I am trying to say, whenever you are analyzing whether equation is linear differential equation with constant coefficient or not, don't bother about the separate function of time. If it is coming, good. If it is not coming, then better, more than good. But it can come. Right now it is not coming, that is different thing. See, and whenever linear differential equation with constant coefficient is coming, now what is the method to find its solution? Solution means the solution of x, because here dependent variable is x. The method to find the equation of x is CF plus PI. This you will study in mathematics. I am not going in too much detail. I am discussing in short manner. Here CF is known as complementary function and PI is known as particular integral. First I am discussing about PI. See, if in this equation some separate function of time is coming, that is independent variable is coming, then PI will come. Okay, and how to calculate that PI you will study in mathematics. But if some independent function of time, some separate function of independent variable, that is time, is not coming, here it is not coming, then PI will always be 0. So since here some independent function or separate function of independent variable, that is time, is not coming, that's why here PI will be 0. So here if we want to find the solution, we need to only calculate CF. But if we are calculating CF now, first you need to find auxiliary equation and you have to find the root of auxiliary equation, because CF depends upon the root of auxiliary equation. What is auxiliary equation? For that now, I am converting this equation in one standard form. How? What I am doing? I am replacing d by dt with differential coefficient capital D. D square by dt square is by d square. D square is not the square of d. It is double order differential coefficient. So then this equation will, this derivation is just for understanding, na? It will become d square x plus c upon m dx plus k upon m x. So x I am taking common equal to 0. So if it is linear differential equation with constant coefficient, now after doing this replacement with this x, you will always get a function of operator d. Okay, right now we already know pi is 0. We have to calculate CF. Now for CF calculation, now what we'll do, we'll write the auxiliary equation. Auxiliary equation means what we'll do, we'll equate the function of d with 0. And here we will treat d as a variable. We'll equate function of d as 0. So equate with 0 and we'll consider d as variable. And if you are considering d as variable, you will get the root of this equation. If it is double order equation, you will get 2 root. And based on the pattern of root, the equation of CF decided. Whether root are real and different, whether root are real and same. Suppose both root are coming -2, -3, means they are real and different. If both root are coming -2, -2, means they are real and same. And whether roots are imaginary. Imaginary means suppose one root is -2 plus 3i, other root is -2 minus 3i. So that is imaginary root. So based on the pattern of root, equation of CF decides. Okay. Now see, this is function of d square plus c upon md plus k upon m, equate with 0, and here consider d as variable. And since it is double order polynomial, we will get 2 value of d, means here we will get 2 root. Okay. Now what is the method to find the root of double order equation? If equation is like this, ax square plus bx plus c equal to 0, the formula to find the 2 value of x is minus b plus minus root over b square minus 4ac upon 2a. This you have studied in your school level mathematics. So here what will be the 2 value of d? It will be minus b. B is the coefficient of d, which is c upon m. So minus c upon m plus minus root over b square means c upon m whole square minus 4ac. A is the coefficient of d square, which is 1, and c is this part k by m upon twice of a. Okay, you will take plus and you will get one root, you will take minus and you will get other root. Now I am bringing this to above side, so it will become minus c upon 2m plus minus. Now here 1 by 2 will come. Now if we will bring 1 by 2 inside root, it will be 1 by 2 is whole square, because root of 1 by 2 whole square is 1 by 2. So inside root it will be 1 by 2 whole square. So here square is already coming, so I am writing c by 2m because it is 1 by 2 square. Now here also 1 by 2 whole square you need to multiply, that is 1 by 4. 1 by 4, so below side 4 will get cancelled with this 4. So ultimately here only k by m will remain. Okay. Now we need to see, if you want to write the solution now, whether we need to see whether this root is real and different, or it is real and same, or it is imaginary. So if you will do proper analysis now, you will find here all possible, all conditions are possible. How? See, if inside this square root negative number is coming, root will be imaginary. If inside this square root 0 is coming, means this part is 0, so both root will be this. Means in that case root will be real and same. And if inside square root positive number is coming, means it will be real and different. So here all conditions are possible. By how? If this term, that is c by 2m whole square, is less than k by m, so can I say inside square root there will be negative number, means root will be imaginary. If this part is equal to k by m, means inside square root it will be 0, means root will be real and same. And inside square root, if this part is greater than k by m, inside square root positive will come, means root will be real and different. So here all these 3 cases are possible. This is very important, na? So I am taking one by one. Case 1, when root will be imaginary. So root of, okay, only try to understand. At last I will make final summary and you have to remember only the final summary. So root of auxiliary equation, here root is very important to find the solution, will be imaginary. Can I say when c by 2m whole square is less than k by m? It is for general case. Similarly, case 2, can I say root of auxiliary equation will be real and same when c by 2m whole square is equal to k by m. Similarly, can I say the root of auxiliary equation will be real and different when c by 2m whole square is greater than k by m. Okay. So if you want to conclude whether root is real and different or it is real and same, it is imaginary. See the relation between c by 2m whole square and k by m. It is less, if this term is less than k by m, root will be imaginary. If it is equal to k by m, root will be real and same. If it is greater than k by m, it will be real and different. Okay. But see, remembering this is very lengthy, na? So what we are doing here, we are defining a dimensionless number term. How? If we bring this k by m below side, can I say it will become c by 2m whole square upon k by m? And can I say for first case it will be less than 1, for second case it will be equal to 1, and for third case it will be greater than 1. So what I am doing, this ratio, that is c by 2m whole square divided by k by m, this dimensionless ratio I am giving a name, because I can tell whether root are real and same or root are real and different or imaginary by using this ratio. If this ratio is less than 1, root will be imaginary. If it is equal to 1, root will be real and same. If it is greater than 1, root will be real and different. So this ratio is known as degree of dampness. Okay. So this ratio is known as degree of dampness. Okay. So here I am defining a term which is known as degree of dampness. In short, I am writing as DOD. Still, I will suggest don't remember this formula. Right now, only understand the concept. You have to remember the formula which I will write in the summary. Right now, only trying to understand the concept. So, degree of dampness is nothing but is the ratio c by 2m whole square divided by k by m. Now, thing is getting simpler. So, now you need not to remember this entire equation. Simply remember, if degree of dampness is coming less than 1, root will be imaginary. If it is coming equal to 1, root will be real and same. And if it is coming greater than 1, root will be real and different. Okay. Now, instead of degree of dampness, now I am defining one more parameter which is known as damping factor. What is this? See, here right now, na, degree of dampness is proportional to c square. Okay. Okay. Now, but if we will take a square root of this, then square root of c square will be c. So after taking a square root of this, whatever term will come now, can I say that will be linear function of c? Okay, linear function of c. So that relation will be more simpler because it will be linear function of c. Okay, and that function I am representing as damping factor. What is damping factor? It is nothing but a square root of degree of dampness. What is the benefit of this? Now, damping factor. See, simply na, it will be linear function of c because degree of dampness is not linear function of c. So if we are able to define linear function, so that is more simpler. Na? That's why I am defining degree of damping factor, which is nothing but a square root of this. But na, there will be no change in this pattern. See, if degree of dampness is less than 1, then its square root, that is damping factor, will also be less than 1. If degree of dampness is equal to 1, if degree of dampness is equal to 1, then its square root will also be equal to 1. Okay. If degree of dampness is greater than 1, then its square root will also be greater than 1. Means there will be no change in pattern. No change in pattern means if damping factor, square root of degree of dampness is damping factor, and if damping factor is coming less than 1, means root will be imaginary. If it is coming equal to 1, root will be real and same. And if it is coming greater than 1, root will be real and different. Okay. So now I am defining one more definition. This is very important, which is damping factor. And we'll remember the relation of damping factor because this is important parameter. Damping factor I am denoting as zeta. Okay. So zeta is nothing but it is simply square root of degree of dampness. Now I am simplifying its expression. For general case, this is the formula to calculate DOD. Just take the square root of this. So square root of c by 2m whole square is c by 2m. Okay. And square root of k by m is root k by m. Now in one way you can represent like this. See, m upon root m will be root m. So can I write this as like this, c root upon 2 root over km? So this is the formula to calculate damping factor zeta for general case. This formula will remember. Okay. Now another way in which you can write the expression of zeta is, can I say here root k by m is nothing but natural undamped frequency of this system. Natural undamped frequency means, I am not saying the frequency of this system. In this system, damped vibration is occurring. So in that vibration, what will be the frequency? For that, I need to find the solution, which I am finding right now. It might be possible due to the presence of damper, no vibration is occurring. But what is omega n? Now, omega n is not the frequency of this vibration. Omega n is the frequency of this vibration, frequency when no damper is attached, means it is natural undamped frequency. Because I will compare this actual vibration with natural vibration. Na? So that's why I am finding the expression in terms of omega n. So omega n is natural undamped frequency. Undamped means if there is no damper, then the natural frequency is omega n. Then the frequency of this vibration is omega n. Okay, which is a constant for this system. Okay. And we already discussed for general spring mass system, omega n is root k by m. So can I say root k by m is nothing but omega n means natural undamped frequency of this system. So if you want, you can replace root k by m by omega n. So this expression will become c upon 2m omega n. Ultimately, both are same expression. This relation will remember. So this is the formula to calculate damping factor zeta. Okay. Now what we will do if examiner is asking degree of dampness? So see, zeta is square root of degree of dampness. So can I say degree of dampness is zeta square? So now don't remember this, just remember this. So this is the formula to calculate zeta. If examiner asking DOD, square of zeta is DOD. Yes. Now there will be no change in pattern. If zeta is coming less than 1, root will be imaginary. If zeta is coming equal to 1, root will be real and same. And if zeta is coming greater than 1, root will be real and different. So now remember this conclusion with zeta only. If zeta is less than 1, root will be imaginary. If it is equal to 1, root will be real and same. If it is greater than 1, root will be real and different. Okay. And here solution will depend whether root is imaginary, real and same, and real and different. Okay. Now what I am doing now? I am doing the naming of various cases. See, when zeta is less than 1 now, for this case, if you will find the solution, you will find now in that solution some periodic term is coming. Periodic term, I will find the solution later, but since I am doing the naming of various cases, that's why I am explaining this before derivation. Okay, when I will find the solution I will find later, but it is 100% sure. In this case, in the solution, we will find some periodic function. Periodic function means, in this case, vibration will occur. Only difference is in natural vibration, amplitude of vibration was constant. But here when you will find solution, you will find if vibration is occurring, the amplitude of that vibration will reduce gradually with time. Reason? Because here damping is providing the damper is providing the damping effect. But in this case, since vibration is occurring, damper is providing the damping, but damping is not that much sufficient that no vibration is occurring. In this case, vibration is occurring. That's why this case is known as under damping. Under damping means, I am not saying undamping. Undamping means no damper. Here damper is present, but still in the presence of damper since vibration is occurring in this case. That's why this case is known as under damping. Under damping means vibration will occur, but its amplitude will reduce with time. Now you need not to remember this much of thing. One case is under damping. Which case? When zeta is less than 1. We have not find the solution, but we know in this case vibration will occur, but its amplitude will reduce with time. Okay. Okay, our team will update. I think it will be start from January or February, but I am not 100% sure regarding that. Yes. Similarly, if root of auxiliary equation are real and same, in this case we will find no vibration will occur. Okay, no vibration. Similarly, if zeta is greater than 1 na, then also we will find that in this case also no vibration is occurring. Very simple. If in this case no vibration is occurring, so if zeta is greater than 1, we are increasing the damping. And since damping is registering the vibration, so in this case if you are not getting any vibration, so definitely after that if you will increase further damping, again there will be no vibration. So whether zeta is equal to 1 or greater than 1, in both case vibration will not occur. Now what we are doing, this case we are referring as critical damping. Critical damping means, can I say it is the minimum required value of zeta for no damping, no vibration, because if zeta is less than 1, vibration will occur. Okay, so it is, since it is the minimum allowable value of zeta for no vibration, that's why this case is known as critical damping. And when zeta is greater than 1, this case is known as over damping. Means damping is more than the just sufficient value of zeta to avoid any vibration. Because if zeta equal to 1, then also no vibration will occur. So if zeta is more than that, means that case is known as over damping. Summary is, in case of critical and over damping, there will be no vibration. But in case of under damping, vibration will occur and its amplitude will reduce with time. Now, here with exam point of view, now, sometime questions comes, what is the type of damping? So in that case, simply calculate zeta. If zeta is less than 1, under damping, equal to 1, critical damping, greater than 1, over damping. That's it. Okay. But if examiner is asking what is the frequency of vibration, so that question is only valid for case 1. Because vibration is occurring only in case 1 when it is under damping. So now the discussion is more important for case 1, because in case 1 vibration is occurring. So first I am discussing case 1. Okay. But before that, what I am doing now? This is the equation of root of auxiliary equation. Na? Root of auxiliary equation is like this. D equal to minus, you can verify, C upon 2m plus minus root over C upon 2m whole square plus K by M. So what I am doing, I am converting this equation in terms of zeta and omega n. Okay, so see, we know this is the formula to calculate zeta, C upon 2m omega n. So can I say from this, C upon 2m is nothing but zeta omega n. Okay, don't remember anything, only understand. C upon 2m is nothing but zeta omega n. So what I can do now, here I can replace C upon 2m by zeta omega n. So it will be minus zeta omega n plus minus root over. It will be zeta omega n whole square. Okay, plus. Now we know omega n is root K by M. So can I say K by M is nothing but omega n square. Now here you can take omega n square to common. If you bring outside root, it will become omega n. So ultimately it will be minus zeta omega n plus minus omega n root over zeta square minus 1. Now you can see when zeta is less than 1, zeta square will also be less than 1. And if it is less than 1, inside square root we will get negative, means root will be imaginary. If zeta equal to 1, inside square root you will get 0, means root will be real and same. If zeta is greater than 1, inside square root we will get positive, means root will be real and different. Okay. Now I am finding the solution for case 1. Case 1 means when it is having under damping. And when system will be in under damping? When zeta is less than 1. Okay. So now whatever concept I am discussing now, that is only valid when zeta is less than 1. So now after that, whatever formula I am deriving, that is valid only for zeta less than 1. Suppose if for question zeta is coming either equal to 1 or greater than, then whatever formula I am deriving, that is not valid. Because now I am doing the derivation by assuming it is under damping, means zeta is less than 1. Now for this case, what will be the solution? So for that, what will be root of auxiliary equation? I know in this case, root of auxiliary equation will be imaginary. Minus zeta omega n plus minus omega n root over zeta square minus 1. But I know zeta is less than 1. So I am 100% sure inside square root will get negative. Negative means root is imaginary. So now how we can write this imaginary root? So for that, what I am doing now, plus minus omega n inside square root. In this term, I am taking minus common. So it will bring minus common. It will become plus 1. And here minus will come. So 1 minus zeta square. Now, can I write this like this minus zeta omega n plus minus omega n? Can I write like this root 1 minus zeta square into root over minus 1? And root over minus 1 is nothing but iota. Root over minus 1 is nothing but iota. So, can I write like this? It is minus zeta omega n plus minus omega n root over 1 minus zeta square iota. So, you can see here root is imaginary. Imaginary. Okay. So, this we already proved. In case of underdamping, root will be imaginary. But this I am discussing when zeta is less than 1. Okay. Yes. Now, what will be the solution? Solution means equation of x, and here equation of x is equal to CF because we already know pi is 0. Okay. Now, for imaginary root, how to write the equation of CF, that things you have studied in mathematics. I am not going in mathematics part. I am directly writing the solution. Okay. Still, if you want to remember now, I am remembering separately. If in linear differential equation with constant coefficient now, if root is coming imaginary, suppose it is like this, alpha plus minus iota beta. Imaginary root will always come in pair. Like if one root is alpha plus iota beta, other root will be alpha minus iota beta. In that case, if you want to write the solution, solution means equation of x now, it will be like this. You can remember a e to the power alpha t sin beta t plus phi. I'm not going to the derivation. Here alpha is this part, and inside sign the coefficient of time is beta, which is this part. What about a and phi? A and phi are arbitrary constant. Arbitrary constant means they are constant, but we don't know their value right now because that will depend upon boundary condition. Okay. So whenever root is coming like this now, this is the way to write the equation of CF. It is the way to write the equation of CF. Okay. But right now CF is the solution because pi is 0. So same formula you can use here. It will be like this, a e to the power alpha. Alpha is minus zeta omega n. So minus zeta omega n t sin beta. Beta is this part, omega n root over 1 minus zeta square t. But how you can remember this equation, I will tell, don't worry. Fine. Okay. So, but this is only valid when zeta is less than 1. Now, what I am doing, you can see now here in this final solution, but this term is periodic. And in this periodic term, this is the coefficient of time. And we know if this periodic term is coming, like if it is sine or cos term is coming, it is simple harmonic term. I am not saying entire equation is simple harmonic because here exponential term is also coming. But I am talking about this term. This is simple harmonic. Na? And in this simple harmonic term, the coefficient of time is known as frequency in radian per second. So can I say for damped vibration, if it is under damping case, can I say this is the frequency of that vibration in damped radian per second? So what I am doing, this frequency I am denoting as omega d. I will make the summary, don't worry, but just try to understand the concept. Because since it is the frequency of damped vibration, frequency in radian per second I denote as omega. And since I am discussing for free damped vibration, I am taking suffix d. So this is nothing but frequency of damped vibration. Omega d, whose equation is omega and root over 1 minus zeta square. So what I am doing, I am writing the equation like this. X is equal to a e to the power minus zeta omega n t sin omega dt plus phi. This equation you can remember easily how I will explain. And we will remember separately the formula to calculate omega d is omega and root over 1 minus zeta square. Okay. Now I am trying to reading this equation. See. Okay. First of all, since it is under damping, and in case of under damping, right now I discussed vibration will occur. And since vibration is occurring now, here some periodic term will come. That's why this term is coming. A sin omega t plus phi. Simple harmonic term is coming. A sin omega t plus phi is phi. But here this omega I am denoting as omega d since we are discussing free damped vibration. So its frequency I will denote as omega d. So instead of omega I am writing omega d. Separately we will remember this equation. This is the formula to calculate omega d. But since in under damping vibration is occurring, that's why this periodic term is coming. But we also know in case of damped vibration, if vibration is occurring, then the amplitude of that vibration will decrease with gradually. Reason? Because damper is providing resistance, so amplitude of each cycle will not be constant. So here, since amplitude will reduce gradually now, that's why with this term one exponential decreasing function is coming, because it will continuously decrease with time. Okay, see what I am trying to say. With each time period this term will repeat. Okay, with each time period this term will repeat. Okay, suppose at t equal to 0, this term a sin omega dt plus phi, suppose x, capital X, just for understanding. After one time period it will also be capital X. But what will happen at t equal to 0 now, if you see this term will be 1. But after one time period this term will be lesser than 1. Suppose it is 0.8. So see this term is repeating in each time period, but this term is reducing. So ultimately the product will reduce now. So that's why what will happen now, amplitude of each cycle will reduce with time due to the presence of this exponential decreasing term. So how you can remember this equation? If you want to remember, you can remember like this. Since here vibration is occurring, so periodic term will come. So that's why a sin omega dt plus phi is coming. Instead of omega I am writing omega d, because it is then vibration. But since amplitude will reduce continuously gradually with time, so that's why one exponential decreasing function is also coming, which is e to the power minus zeta omega and t. Like this you can remember this equation. Okay, now if we draw the graph of this equation now, it will be like this. Okay. I am directly drawing the graph. Okay, you can see it is the product of this term and this term. So due to the presence of this term, can I say in each time period amplitude will reduce gradually. So what will happen now? Here if you draw the graph, it will be like this. To and fro motion is occurring, but its amplitude is continuously reducing with time. Like this. Means it will take two corresponding point. Corresponding point means with one time period gap. Suppose I am taking the amplitude of initial cycle. Then I am taking amplitude after completing one cycle. Then again after completing one cycle. So you will find here if it is capital X0, it is capital X1, it is capital X2. So capital X1 is less than capital X0, capital X2 is less than capital X1. Okay. Okay. Now with each time period, why displacement or amplitude is reducing? Due to the presence of this exponential decreasing function. So here in this graph now, it will join the points after one time period. One time period means, see here frequency is omega d na, so time period will be 2 pi by omega d. So if you are joining the points after one time period na, this will be exponential decreasing curve. Because value after one time period is reducing due to this point. Okay, and that is not only valid for this amplitude point. You can take any 2 points. Suppose one point I am taking this point at t equal to 0. Now take next point after one time period. Take next point after one time period. Again, if you join this point now, in which the gap is one time period, that curve will be exponential decreasing curve. Because after one time period, value you are getting lesser due to the presence of this. So this is the graph of free damped vibration in case of under damping. Okay, but what type of questions can come here? So if question is coming, generally examiner will ask, since here vibration is occurring, so what is the frequency of this vibration? That I am denoting as omega d if you are calculating radian per second, and formula to calculate omega d is okay. See, if I will ask frequency means frequency of free damped vibration in radian per second. This is only valid when zeta is less than omega d. The formula to calculate omega d is omega and root over 1 minus zeta square. Okay. Now, if we calculated frequency in radian per second, means you can calculate frequency in hertz also. Frequency in hertz. Suppose that I am denoting as fd. It is omega d upon 2 pi. You can calculate time period also. Time period I am denoting as td. It will be 2 pi by omega d. Time period means time to complete one cycle of this vibration. Okay, yes. Now here, this is one question which can come, calculate the frequency or time period. Very easy, it is very easy, na? Yes. Next question which can come na, in free band vibration, if it is under damping na, it will take the display amplitude of 2 consecutive cycle. So if it will take amplitude of 2 consecutive cycle, can I say time gap between them will be 1 time period? So after 1 time period, you are getting displacement lesser. Reason? After 1 time period, we are getting the displacement lesser due to the presence of this term. So what will happen now? Here you will get a interesting result, which is, I am writing here, the ratio of amplitude of 2 consecutive cycle or it is not only for amplitude, you can also write ratio of displacement of corresponding point. When I am saying corresponding point na, means I am saying the time gap between them is 1 time period in 2 consecutive cycle. So see, suppose the displacement of any point in initial cycle I am denoting as x0. If it is amplitude represent as capital X0, then suppose displacement after 1 time period is x1. Similarly, suppose displacement of any point after completing 1 cycle is x1. Then displacement after completing 1 more cycle is suppose x2. Okay. So you'll see now the time gap between these 2 displacement is 1 time period. And time gap between these 2 displacement is also 1 time period. So if time gap, whichever ratio you are taking now, in that displacement ratio, if time gap is 1 time period, so in this case, this ratio will always be constant. Okay, whether you are taking x2 by x3, x3 by x4, or xn minus 1. Xn minus 1 means it is the displacement of any point in n minus 1 cycle after completing this cycle. Okay. Upon xn is displacement of any point after completing n cycle. So this ratio, only remember, in this ratio na, earlier displacement I am taking above side and later displacement I am taking below side. And if time gap between them is 1 time period, this ratio will be constant and it will be equal to e to the power 2 pi zeta, I am not going in derivation, upon root over 1 minus zeta square. I am not going in derivation, just remember. Right now don't remember this. Only understand. At last I will make the summary. But if you will do proper derivation, this relation you will get. Okay. But it is little bit complicated. Na? This ratio is constant, but this is equal to e to the power 2 pi zeta for root over 1 minus zeta square. So what I am doing now? First I am defining this term separately because it is bigger function. This term I am denoting as delta. You can take any notation. Okay. So if you are remembering that this term is delta, na, then you can easily remember the ratio of displacement of 2 corresponding point in 2 consecutive cycle will be constant and this ratio will be equal to e to the power delta. Okay. And this delta is known as logarithmic decrement. Why I am explaining? But simply this formula to calculate delta is this. Why delta is known as logarithmic decrement? Because logarithmic decrement. See, if I am referring this as delta, this ratio is e to the power delta. Now I will take both side log of base e. It will be log x0 by x1 or log x1 by x2 or log xn minus 1 upon xn. And can I say this log will be equal to delta log e, and log e base e is 1. So can I say log of x0 by x1 is nothing but delta. Now see, if we are referring x0 by x1 as decrement because with each cycle displacement reducing, can I refer log of that as logarithmic decrement? So with this logic we are referring delta as logarithmic decrement because delta is nothing but it is log of xn minus 1 upon xn, means log of ratio of displacement of 2 consecutive cycle. And the formula to calculate delta is always 2 pi zeta upon root over 1 minus zeta square. So this formula will remember. And whenever examiner is asking ratio of displacement in corresponding point in two consecutive cycle or ratio of amplitude in consecutive cycle, that ratio will always be equal to e to the power delta. First through this formula calculate delta, then this ratio is e to the power delta. So now can I write the ratio of displacement in corresponding point in consecutive cycle is constant, and this is equal to e to the power delta. Okay. Now here I am discussing one more interesting result. If you are calculating x0 by x1, means if time gap between them is 1 time period, it is e to the power delta. Similarly, sometime examiner can ask x0 by x3. So see, time gap between them is 3 time period. See, can I write like this? It will be equal to x0 by x1 into x1 by x2 into x2 by x3. Can I write like this? Now we know x0 by x1 is e to the power delta. x1 by x2 is also e to the power delta. It is also e to the power delta. So ultimately it will become e to the power 3 delta. So ultimately, can I say whatever displacement ratio I am taking, in that ratio, time gap is 1 time period. Only remember, earlier displacement should be above side, later displacement should be below side. Then this ratio is e to the power delta. Similarly, in this ratio, if time gap is 3 time period, it will be e to the power 3 delta. Similarly, can I say in this ratio, if time gap is n time period, means we are calculating x0 by xn, can I say it will be equal to e to the power n delta. And this is the formula to calculate delta, which is 2 pi zeta upon root over 1 minus zeta square. Okay. So this is very important discussion. Now I am making the final summary, and just remember the summary. The summary is, first of all, but this is summary for general case, na? For general case, the governing equation is like this: mx double dot plus cx dot plus kx equal to 0. In this equation, the coefficient of x is k, which is the stiffness of a spring, but it is for general case. Coefficient of x dot is c, which is the damping coefficient of the chamfer, and coefficient of x double dot is m, which is the mass. Okay, and as per this equation, if you want to find its solution, mainly find two things. One is zeta, which is nothing but damping factor. Formula to calculate zeta for general case. This is for general case, c upon 2 root over km or c upon 2m omega n, and see whether zeta is coming less than 1, equal to 1 or greater than 1, because it will decide the type of damping. Similarly, if you are doing calculation, also calculate omega n, because later we had derived the formula in terms of zeta and omega n. Omega n is not actual frequency. It is natural undamped frequency. Means if no damper is there, then what will be the frequency? That I am denoting as omega n. So it will be, it is not, for general case, the formula to calculate omega n, we already know it is root k by n. Now, if we calculate zeta, now sometime examiner can ask degree of dampness also. Then you can calculate degree of dampness also. It is zeta square. Now, most important thing is, if zeta is less than 1, it is under damping. In under damping, vibration will occur. That's why this case is very important. That's why this case I discuss in detail. Okay. Now, if zeta is equal to 1, it is critical damping. In critical damping, no vibration will occur. Okay. Similarly, if zeta is greater than 1, it is over damping. In over damping also, no vibration will occur. That's why question will never come in which examiner has calculated the frequency when zeta is greater than 1. It is incorrect question, because in free band vibration, if zeta is greater than 1 or equal to 1, no vibration will occur. If you want, you can simply write here also, no vibration will occur or no oscillation will occur. Here also, no oscillation will occur. But since in case when oscillation is occurring, that's why this case I discuss in detail. So now if we discuss the case of under damping, now whatever formula I am writing, that is valid only for under damping, means when zeta is less than 1. In this case, you will find the solution now. It will be like this. Here, first periodic term will come. So it will be like this: a sin omega t plus phi. Instead of omega, we are writing omega d, because it is damped vibration. So frequency we are denoting as omega d. But here periodic term is coming because in this case vibration will occur. But here amplitude of vibration will not constant, it will reduce gradually with time. For that, with this one exponentially decreasing function will come, which is e to the power minus zeta omega n t. So you can remember the solution like this. Next, If examiner asking it's calculate its frequency, that is frequency in radian per second, then formula to calculate omega d is omega and root over 1 minus zeta square. Now, if we calculate frequency in radian per second, you can calculate frequency in hertz also. It will be omega d by 2 pi. You can calculate time period also. It will be 2 pi by omega d. Next important is calculation of logarithmic decrement delta. The formula to calculate delta is 2 pi zeta upon root over 1 minus zeta square. What is the significance of this? In case of underdamping, we know the ratio of displacement of two consecutive cycle or ratio of amplitude of two consecutive cycle will always be constant, and in this ratio, if we are taking earlier displacement above side, later displacement below side, this ratio is also equal to e to the power delta. Similarly, in this ratio, if gap is nth time period, like we are calculating x0 by xn, then this ratio is equal to e to the power delta. Yes, so this is the final summary. So if question is coming regarding general case, you can always solve. First calculate zeta. If it is less than 1 underdamping, then this all formula are valid. If it is equal to 1 or greater than 1, if it is equal to 1, critical damping. If it is greater than 1, over damping. And in both critical and over damping, no vibration will occur. Okay. So this is the final summary. Now we'll solve some questions. Okay. Like first we have to solve this question. This is multiple choice question. In this question, this diagram is given. You have to tell what is the type of damping, whether it is under damping, critical, over, or you cannot say. So simply calculate zeta. If it is less than 1, it will be under damping. If it is equal to 1, critical. If it is greater than, over damping. And this is general case, na? Because spring is directly attached to the mass, parallel to this damper is attached. So for general case, we know direct formula, na? Okay. See. The stiffness of this spring, that is K is given, it is 300, use SI unit, na? Newton. If it is given in Newton per mm, convert in Newton per meter. Use SI unit. The damping coefficient of the damper, suppose I am denoting as C, it is 200 Newton second per meter. The mass is 20 kg. Now calculate just zeta. For general case, formula to calculate zeta is C upon 2 root over Km. Now C is 200. Upon 2 root over Km, K is 300, M is 20. How much zeta is coming? 200 divided by 2 into root over 300 into 20. It is coming 1.291. It is coming 1.291, which is greater than 1. And since zeta is greater than 1, it is over damping means here no vibration will occur. So for this question, the correct answer is option C. Very simple. Now next, this is the question. In this question, equation of vibration is given. So simply if equation is given, you can compare with the equation mx double dot plus cx dot plus kx equal to 0. Because same equation is there. So you will get the value of m, c, k, and you can calculate anything. So examiner is asking frequency in hertz. So first we'll calculate frequency in radian per second, then you can calculate frequency in hertz also. But here examiner asking frequency na, I am 100% sure this will be under damping case. Because if it is critical or over na, no vibration will occur. So for this question, whatever zeta will come na, I am 100% sure it will be less than 1. Because if it is not less than 1, then this question is incorrect. Let's see. Here equation is given like this na, 4x double dot plus 8x dot plus 25x equal to 0. Just compare this equation with mx double dot plus cx dot plus kx equal to 0, because both equations are same na. So you can use the same solution. Here instead of m 4 is coming, instead of c 8 is coming, and instead of k 25 is coming. So in the formula of zeta, omega and whatever formula you are using, instead of k put 25, instead of c put 8, and instead of m put 4. So what I am doing, first I am calculating zeta. So formula to calculate zeta is c upon 2 root over km. Here instead of c we are putting 8 upon 2 root over km. K is 25, m is 4. So 25 into 4. How much zeta is coming? 8 divided by 2 root over k, 25 into m4. Is it coming? 0.4. You can check the calculation. Yes. And whatever it is coming, it is less than 1, means it is underdamping. Underdamping means here vibration will occur, so this question is relevant. Now, to calculate frequency, calculate omega n also, because we know the formula in terms of zeta and omega n. So omega n will always be root k by m for general case. Omega n root over k. K is I think 25. Yes, and m is 4 na. So 20 by 4. How much omega n is coming? Root over 25 by 4. That is 2.5 radian per second. Okay. Now, our objective is to calculate frequency of this vibration is hertz, that is fd. And can I say fd is nothing but omega d upon 2 pi? I am directly calculating frequency in hertz. And what is the formula to calculate omega d? It is omega and root over 1 minus zeta square. So for this we can calculate omega d, and omega d divided by 2 pi is fd, that is frequency in hertz. Now omega n is 2.5 into root over 1 minus zeta square. Zeta is 0.4, its square divided by 2 pi. So how much frequency of this vibration in hertz is coming? 2.5 into root over 1 minus 0.4 square divided by 2 divided by pi. It is coming 0.365 hertz. Okay. So frequency of vibration in hertz is coming 0.365. Okay. So like this you can solve the question now. Like this is the next question. For a critical damped means zeta is equal to 1. Single degree of freedom system, damping coefficient is 4 Newton second per meter. Spring constant means stiffness is 16 Newton per meter. So what will be the mass? See, whenever question is coming like this, and if diagram is not given, so if diagram is not coming, always consider general case. And if you are considering general case, you can use the formula of general case na. So here in this case, the damping coefficient is C is 4 Newton second per meter. Stiffness of the spring K is 16 Newton per meter. Mass is unknown, but it is given it is critical damp. Critical damp means zeta equal to 1. Now, if you are considering general case, if diagram is not given, always consider general case. And for general case, formula to calculate zeta is C upon 2 root over Km. And write down since it is critical damp, zeta will be 1. Now, from this C and K is given, only unknown is M, so we can calculate M. C is 4 upon 2 root over K is 16 into M equal to 1. So this part will come this side. So 4 divided by 2 is 2 equal to root 16M. We will take a square of both sides. Square of 2 is 4 equal to 16M. So how much M will come? It is coming 0.25 kg. You can check the calculation now. Okay. So the required value of mass M is 0.25 kg. Matching with which option? So this is correct answer for this question. So like this you can solve. Very easy na? If you understood na, summary. Now this question, what this question is saying, for a damped spring mass system, mass is 10 kg, stiffness is 10 to the power 3 Newton per meter, damping coefficient is 20 kg per second. Then what is the ratio of amplitude of oscillation in 2 consecutive cycles? 2 consecutive cycle means time gap between them will be 1 time period. Okay. So see, again we are considering it is general case. Even if M is 10 kg, use SI unit. K is 1000 Newton per meter and C is 20 kg per second. See, I had discussed unit of C is Newton second per meter, SI unit. So you can represent Newton second per meter also as kg per second. Both are same, na? How? Just use the unit balance. See, this is just for understanding, because you will tell na, sir, earlier you told unit of C is Newton second per meter, but why here it is given in kg per second? So see, Newton second per meter. Now see, Newton is the unit of force. Force is nothing but unit of force is also the unit of mass into acceleration, because indirectly mass into acceleration is also force, na? And unit of mass is kg, unit of acceleration is meter per second square. So Newtons you can write like this, kg meter per second square. Now into second, and this meter is already coming. So mm will get cancelled, 1s will get cancelled. So it will be kg per second. So it might be possible sometimes C is instead of Newton second per meter, examiner is giving kg per second. So if you want, you can replace kg per second like this. Now calculate zeta. Zeta is C upon 2 root over km. C is 20 upon 2 root over km. K is 1000. M is 10 kg. How much it is coming? Root over 1000 into 10. 0.1. It is less than 1, means under damping. Na? So this question is again relevant. Exam asking ratio of amplitude of two consecutive cycle, means whether you say capital X0 by X1 or X1 by X2 or Xn minus 1 upon Xn. It is equal to e to the power delta. Okay. So e to the power delta. And delta is logarithmic decrement. So first I am calculating delta. Formula to calculate delta is 2 pi zeta upon root over 1 minus zeta square. So from this I can calculate delta. 2 pi zeta. Zeta is 0.1 upon root over 1 minus zeta square. Zeta is 0.1. So it is square. How much delta is coming? 2 pi into 0.1 upon root over 1 minus 0.1 square. Delta is coming 0.6315. You can check the calculation. Na? Calculation is your part. Just put here. So this ratio will be e to the power 0.6315. How much it is coming? It is coming 1.88. Okay. So we have completed the general case of free band vibration. Now, how we'll deal with the problem of other cases? Other case means that if diagram is given, and whichever diagram is given, it is other than the diagram of general case. So for that, what will we do now? First, we'll derive the governing equation of vibration. Governing equation of vibration. See, for general case, equation of vibration was like this: mx double dot plus cx dot plus kx equal to 0. This also we come to know after derivation. But for general case, we remember this. The coefficient of x is k, which is the stiffness of spring. Coefficient of x dot is c, which is the damping coefficient of damper. And coefficient of x double dot is m, which is the mass of the point mass. But for other case now, if it is free band vibration, the pattern of equation will be like this, because it is free band vibration. But here coefficient might change. And that will come to know after derivation. After derivation, we have come to know na, that for general case, coefficient of x is k, coefficient of x dot is c, coefficient of x double dot is m. But what will be this coefficient for other case, that will come to know after derivation. So see, for other case, whatever coefficient of x will come, na, that I am denoting as ke. Okay, k. Ke is not stiffness of the spring. For general case, k is k. But for other case, Ke can be KL square, Ke can be K by 2, Kb can be K by 3, Ke can be in terms of G, that is gravity. So what will be Ke? That will come to know after derivation. For general case, Ke is equal to K. Similarly, the coefficient of x dot I am denoting as C. For general case, C is equal to C, but for other case, it doesn't necessarily C will be C. It can be C by 2 also, it can be CL square also, it can be C also, but that will come to know after derivation. Similarly, the coefficient of x double dot for general case is m, but whatever this coefficient will come for other case, that I will denote as me. Me is not mass. Me can be mass. It can be mass by 2. It can be ml square. It can be inertia. That will come to know after derivation. Okay. For general case, you can say m is m, c is c, k is k. Okay. And now it's not necessary here always x dot x double dot will come. Here if it is theta, it should be theta dot, it should be theta double dot. If it is phi, it should be phi dot, phi double dot. Then all equations are same. Like here, if it is theta, it should be theta dot, it should be theta double dot. Then see the coefficient. Coefficient of acceleration I am referring as me. Coefficient of theta dot I am referring as c. C is not c. C, what is c? That will come to know after derivation. And coefficient of theta I am referring as k. Okay. Now, how will find the solution? We need not to do entire derivation. Just remember one analogy. For general case, whatever formula we have derived now, in that formula at the place where Ke was coming, can I replace that with Ke? At the place where C was coming, I can replace that with Ce. And at the place where M was coming, we'll replace that as Me. For general case, Me was M, Ce was C, Ke was K. For other case, what will be Me, Ce, Ke? That will come to know after derivation. Okay. Like, see, what is the formula to calculate zeta? The formula to calculate zeta is C upon 2 root over Km, but it is for general case. For other case, instead of C, CE will come, 2 root over. Instead of K, KE will come, instead of ME will come. And we will get to know expression of CE, KE, ME after derivation. Okay. After that, entire solution is same. Like, what is the formula to calculate omega? And for general case, it was root K by M. But for other case, it will be root KE by ME. For general case, K is K, M is M. So just replace C by C, K by K, M by ME. Then the solution will be same as general case. Only difference, instead of C, C will come, instead of K, K will come, instead of M, ME will come. That's why now I had derived entire formula in terms of zeta and omega n. Because once you have calculated zeta and omega n, rest of the discussion will be same. Means if zeta is less than 1, it will be under damping. If it is greater equal to 1, greater damping, it is greater than 1, over damping. In critical and over, no vibration will occur. In under damping, vibration will occur, but its amplitude will reduce with time. If it is under damping, examiner asking calculate its frequency in radian per second, that is omega d. The formula is omega n root over 1 minus zeta square, and we already calculated omega n and zeta. Okay. Okay, if you are asking logarithmic decrement delta, formula is 2 pi zeta upon root over 1 minus zeta square. If you are asking ratio of displacement in two consecutive cycle, it is e to the power delta. Okay, so we have remembered all the formula in terms of zeta and omega. So first calculate zeta and omega, and after that discussion is same as general case. Only difference, instead of C, C will come, instead of K, K will come, instead of M, M will come. Or you can simple remember, this is the final formula. For general case, C is K, K, C, K is K, M is M. But for other case, what will be C, K, E, M E, that will come to know after derivation. Okay. But to use this, first we need to find M E, C, K, E. For that, I need to do the derivation. And to derive the equation of vibration, in damped vibration, we can use only one method, that is equilibrium method. Like in natural vibration, we were using one more method, which was energy method. But energy method is not valid for damped vibration, because in energy method, we were taking an assumption that during vibration total energy is constant. But here, since damper is present, during vibration total energy will not be constant, it will reduce gradually with time. So to derive the equation of damped vibration, we can use only one method, that is equilibrium method. I am discussing some questions, like I am discussing this question. In this question, this diagram is given. Okay. In this diagram, you have to tell what is the type of damping, whether it is under damping, critical damping, over damping, or you cannot say. So just calculate zeta if it is coming less than 1, under, equal to 1, critical, if it is greater than 1, over. But here, don't say formula to calculate zeta will be C upon 2 root over Km. No, 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 no. That is not general case. So I need to derive the equations. How will derive? So see, here I am doing discussion. Directly with question, I am doing the discussion. See, here this system will have rotational vibration. Okay, and last lecture I told was the lecture of rotational vibration, because rotational vibration in YouTube I have already discussed for natural vibration case. So I am hoping you have watched that lecture. If you have watched those lecture, this you will understand very easily. Okay, here only difference is it is not natural vibration, it is damped vibration, because damper is also attached. Now what we do now, whenever system is having rotational vibration, it is vibrating with rotations. So for the body whose inertia is given, right now the mass of this rod is given. The mass of this rod is capital M. It is not clearly visible, I am writing. Mass of this rod is capital M. Here this linear spring is attached, whose stiffness is K. Here this damper is attached, whose damping coefficient of C. And here this torsional spring is attached, whose torsional stiffness is KT. And the values are given. Here the mass of the rod M is 10 kg. Damping coefficient of the damper, that is C, is also given. It is 500 Newton second per meter. Convert in SI unit. Okay. The stiffness of this linear spring K is 2 Newton per mm. But convert this in SI unit, that is in Newton per meter. So 2. See, above side already Newton is coming, but below side mm is coming, and we have to calculate mm in meter. And 1 mm is 10 to the power minus 3 meter. So below side write 10 to the power minus 3. So it is in Newton per meter. It will be 2000 Newton per meter. Similarly, the stiffness of this torsion spring KT is also given. It is 1 kilonewton meter per radian. Convert this in SI unit, means Newton per meter per radian. So 1 kilonewton is 1000 Newton. So it will be 1000 Newton meter per radian. Now I am doing the derivation. So first, for the body whose inertia is given, inertia of this rod is given, find the I center of that body. I am hoping you have watched the lecture of rotational vibration, na? In which I discuss natural vibration for rotational vibration. If you watch that lecture, it will be very easy. Okay. So what we'll do now, first we'll find the I center of this rod. I am using I center method. Now what is I center? Just remember, I center is the imaginary point about which you can assume this body is rotating. Okay. And if any rod is hinged at any location, like right now this rod is hinged at this location. So this hinge point will always be the location of I center. This hinge point will always, because this rod will rotate about this point, na? Because it is hinged here. So it is the location of I center. Okay. Now whenever you have located I center, na, I will always suggest calculate, this rod is rotating about I center. So calculate the mass moment of inertia of this rod about I center, because this will be required during derivation. How, when we'll do derivation, we'll come to know. But first calculate the mass moment inertia of this rod about I center. Now how I can calculate mass moment inertia of this rod about I center? This is simple mechanics. See, whichever formula I am using now, I am writing here. See, first remember the formula to calculate mass inertia of the rod. Suppose the mass of the rod is m, length is l, about its center of gravity. Center of gravity of the rod will be at the middle. So see, for this thin rod, the formula to calculate I about center of gravity is ml square by 12. Just remember this formula, where m is the mass of the rod, l is the length of this rod. But this is about center of gravity. But what is the formula if you want to calculate mass inertia of this body about any other point? So for that we will use a theorem which is known as parallax theorem. What is parallax theorem? Suppose for any body, you know the mass inertia of that body about center of gravity. Suppose that I am denoting as Ig. For rod, this formula was ml square by 12. Na? But for the same body, if you want to calculate mass inertia about this point, when I am saying about this point, na, means we know the mass inertia of this rod about center of gravity, okay, which is perpendicular to the rod, means which is about, means suppose this axis I am referring as z axis. So when I am saying mass inertia about center of gravity, means mass inertia about the z axis passing through G. But I want to calculate mass inertia about A, means mass inertia about z axis which is passing through A. So for that we will use a theorem which is known as Parallax theorem. In Parallax theorem, what we will do now, whichever 2 point you are taking, one point should always be center of gravity of that body. Now here other point is point A. The formula to calculate mass inertia about point A is always first calculate mass inertia of the same body about center of gravity, that is Ig. In this theorem, always in RHS will take I about G. Now to calculate I about A, in Ig will add mr square. So m is the mass of this rod or body into, I am referring this as r dash. So r dash square. What is r dash? It is radial distance between center of gravity and the point which you have taken in left hand side. Okay, so this distance is r dash. So now here I want to calculate mass inertia of this rod about I center, na. So what we'll do? First calculate I about I center. First calculate mass inertia of this rod about center of gravity. If center of gravity is not coinciding with I center, use Parallax theorem. So first locate the center of gravity of the rod. Center of gravity of the rod will be at middle. Now suppose length of the rod I am denoting as L, it is 0.5 meter. 0.5. This is point. I had not drawn the diagram by using scale. Na. Actually, na 0.4 meter is very near to 0.5. Okay, I am drawing. Suppose I am drawing with proper scale. I am showing the damper this side because 0.4 is near to 0.5. Na. So this is 0.4 meter. Now, see, the center of gravity of the rod will be at middle. Middle means it will be at a distance L by 2 from here, which will be 0.5 by 2, that is 0.25. So it will be somewhere here. Na? So this is the location of center of gravity, and this distance is L by 2, or you can, if you want to write directly value, it is 0.25 meter. Okay. Now, for rod, mass of rod about center of gravity is ml square by 12, but it is about center of gravity. Now, to calculate about I center, I am using I center, Parak's theorem. So, in this, I am using adding mr square. So, m is the mass of the rod into r. R is the radial distance between center of gravity and I center, which is L by 2. So, it will be L by 2 whole square. Now, if you simplify this, now it will come ml square by 3. You can check simplification. Okay. And here m is 10 kg, L is 0.5 meter. So, ultimately, it will be 10 ml square by 3 into 0.5 square divided by 3. So, how much I about I center is coming for this rod? 10 into 0.5 square divided by 3. It is coming 0.833 kg meter square. Here you will put directly value, na, you will get same answer. So, this is I about I center. Okay. Now, if you are deriving the vibration equation, na, during vibration, take any position in which this rod has rotated about I center by theta angle. Okay, theta angle. But before that, again make one conclusion, whether restoration will occur due to gravity or not. This is important conclusion. Since here spring are attached and two spring is attached. Now, one is this linear spring, one is this torsion spring. So, definitely restoration will occur due to spring. There is no issue. But restoration will occur due to gravity or not. Because if restoration is not occurring due to gravity, during the derivation of vibration equation, neither will consider weight nor will consider static deflection of the spring due to weight. But if restoration is occurring due to gravity, then we have to consider weight also. So, see, here now, if this spring we are not attaching now, this rod cannot remain in this place. So, can I say weight of this rod are supported by this spring? And since weight of the rod are supported by spring, can I say here due to weight there will be static deflection in the spring? And since due to weight there will be static deflection in the spring, so can I say they will counter each other effect? And since they are countering each other effect, means there will be no role of gravity in the restoration. And since there is no role of gravity in the restoration during derivation of equation of vibration, neither will consider weight nor will consider static deflection of the spring due to weight, because they are cancelling each other effect. But how they are cancelling, don't bother about that. Okay. So, now I am taking any position in which this rod has rotated by theta angle about I center, and this theta is from mean position, because we need not to bother about the displacement of mean position. Now, you can take theta clockwise also, anti-clockwise also, it is your will. So, suppose I am taking any position in which this rod has rotated by theta angle about I center in clockwise direction. This theta is very small. For understanding, I am drawing diagram little bit bigger. This is from mean position. Now, here damper is attached. So, due to this rotation, suppose displacement of this point is x1. Here spring attached. So, therefore, displacement of this point is x2. We can find the expression of x1 and x2 in terms of theta. This derivation I am doing for small oscillation. Small oscillation means theta is very less. How? If you want to find the expression of x2, now just see, it is the displacement of this point. So, what is the distance of this point from I center? It is 0.5 meter. So, for small oscillation, x2 will be 0.5 theta. Actually, now, after displacement, this distance is 0.5 meter. So, we will calculate x2, now it will come 0.5 sine theta. But when theta is lesser, now you can write sine theta as theta. So, that's why for small oscillation, you can write direct expression. Distance of this point from I center is 0.5, so x2 will be 0.5 theta. Similarly, if you want, you can write the expression of x1 also. It will be 0.4, because distance of this point from I center is 0.4 meter. So, it will be 0.4 theta. Now, here what I am doing, I am drawing the FBD of this displaced position of the rod. And in this displaced position, we will apply all the forces and movement. First, we will apply restoration. And here restoration is coming due to spring. So, apply a spring force or spring movement, because they are restoration. Okay. See, here linear spring is coming. So, due to linear spring, always restoring force will come. And what is the formula to calculate that force? It is very simple. If the displacement of spring from mean position is x, restoring force is kx. In the FBD of this rod, it will be opposite to x. So, right now the stiffness of this spring is k. Its displacement from mean position is x2. So can I say here restoring force will come, which will be Kx2, and it is opposite to x2 in the ability of rod. Right now x2 is downward, so it will be upward. But here along with this linear spring, this torsion spring is also coming. Okay. Now you can remember, like due to linear spring, na, restoring force comes into picture. Na. Similarly, if it is torsional spring, due to torsion spring, instead of force, moment will come. Like if stiffness of linear spring is K, its displacement is X, so force is Kx. In case of torsion spring, instead of K, Kt will come, which is the stiffness of torsion spring. And instead of linear displacement, that is X, angular displacement will come. Suppose that I am denoting as theta. And this Kt theta is restoring moment, and it will always be opposite to theta. If theta is clockwise, it will be anti-clockwise. If theta is anti-clockwise, it will be clockwise. So here, since it is torsion spring, due to this restoring moment will come. It will be equal to stiffness of this spring, which is Kt. Now see its angular displacement. Angular displacement is theta. So this restoring moment will be Kt theta, and it is already a moment. And it will be opposite to theta. Right now theta is clockwise, so it will be anti-clockwise. That's it. But since restoration is not occurring due to gravity, that's why I am neither considering weight nor I am considering static deflection of the spring, because they will cancel each other effect. So restoration part is completed. Now see damping force, because damper is attached. And damping force calculation is very easy. See, the damping coefficient of this damper is C. Yes. Now see its velocity. So see, damper is attached here. Now displacement of this point is x1, but in damping force velocity is required. So can I say if displacement is x1, velocity will be x1 dot. So damping force will be C x1 dot. Okay, and it will be opposite to x1 dot. Now see, if we are calculating x1 dot by differentiation, na, direction of x1 dot will be same as x1. Right now x1 is downward, so x1 dot is also downward, and damping force is opposite to x1 dot. So since x1 dot is downward, it will be opposite to x1 dot, means it will be upward. So this is damping force, but here x1 dot is coming, but this is the expression of x1. So through expression of x1 you can calculate x1 dot also. How? Differentiate this entire equation with respect to time. So differentiation of x1 with respect to time is x1 dot, that will be equal to 0.4, and differentiation of theta with respect to time is theta dot. Yes. So this is about damping force. No other damper is attached, so this part is also completed. But now, right now I cannot use the equation of equilibrium, because this system is not in equilibrium. If you want to use the equation of equilibrium, you need to apply inertia force or inertia moment. Now, if you want to don't do the things, if you want that your derivation is, you want to make derivation simpler, if you don't want to do the complicate the things, I will suggest for derivation always use I center method. In I center method, what we'll do now, after applying the inertial moment, how I will apply that, how we will apply inertial moment, that I will discuss. But after considering inertial effect, we'll always take summation of moment about I center. And if we have calculated applied inertial moment, equate this with 0. See, but I will equate this with 0 after considering the inertial moment. Okay. And if we are using always I center means if we are taking this oath, whenever in any system either rotational or rotational plus translation vibration will occur, na, in that case to derive the equation of vibration, if we are taking always moment about I center, then we'll always apply only inertial moment in this case. And what is the method to apply inertial moment? Like in case of translation, inertial force comes, na, whose expression is mass into linear acceleration. So here instead of inertial force, we'll apply inertial moment, which is instead of mass moment of inertia will come, but that mass inertia will come about I center. And mass inertia about I center I am denoting as II, na. So instead of M, I will come, which is mass inertia about I center. Similarly, instead of linear acceleration, angular acceleration will come. Suppose angular acceleration I am denoting as alpha. So it will be I into alpha. And the direction of inertial moment will always be opposite to alpha. It will always be opposite to alpha. Okay. So apply inertial moment like this. But this concept is valid whenever you are taking moment about I center only. If you are taking moment about other point, concept will change. But if you are taking moment about I center, because this is simpler, always apply inertial moment at I center. And what is the formula to apply inertial moment? I about I into angular acceleration. That's why I have calculated I about I. Already calculated, na? This is I about I. So see, if you want to use I center method, apply inertial moment at I center, whose formula is I about I of this rod into angular acceleration. Now see, angular displacement of this rod is theta. Right now theta is clockwise. So can I say angular velocity will be theta dot, angular acceleration will be theta double dot. And since we are calculating theta double dot and theta dot by differentiation, its direction will be same as theta. Right now theta is clockwise. So theta dot, theta double dot is also clockwise. So inertial moment will be I about I angular acceleration, which is theta double dot. And since it is movement, it will be opposite to theta double dot. Right now theta double dot is clockwise. So it will be anti-clockwise. That's it. And after applying this inertial moment, you can use calculate summation moment about I center. And after applying this inertial moment, you can equate this with 0. Now you say, sir, when you will use this equation, I require the reaction of this hinge support. Yes, but you do not to bother about the value of this reaction. Reason? Because at hinge support, always force reaction will come. And right now we are talking moment about I center. So can I say moment of this force reaction about I center will be 0 because their perpendicular distance from the I center is 0 because they are acting at I center. And formula to calculate moment due to force is force into perpendicular distance. So distance of this force from I center is 0. That's why their moment will about I center will be 0. So you need not to bother about the reaction which is coming at I center. So now I am using this equation. Just use this. One by one. First I am taking this inertial moment, I about I theta. It is already a moment now, so it will come as it is in moment equation, I about I theta double dot. And its direction, it is anti-clockwise. Whatever first direction is coming now, I am taking that as positive. So if I am taking anti-clockwise positive, take clockwise negative. So I am taking anti-clockwise plus na. Now don't say, sir, it is acting at I center, so its moment will be 0 na, because it is, my friend, it's not a force. It is already a moment, that's why it is coming as it is. If it is a force, then I will use this formula. Force into perpendicular distance is a moment. But it is already a moment. Okay. Now, next I am taking moment due to damping force, one by one. So, this is force. Now, this is force. So, moment due to this will be force into perpendicular distance. So, this force is Cx1 dot. Now, see its perpendicular distance from I center. It is vertical, so horizontal distance. It is 0.4 meter. So, moment due to this force about I center will be Cx1 dot into 0.4 meter. Now what is the direction of this moment? So this force is like this. How it is rotating about I center? Anti-clockwise. For anti-clockwise I am using plus. So here plus sign will come. Okay. Now take the moment due to restoration. To restoration is coming. This is restoring moment. Now since it is moment, it will come as it is. This moment is kt theta anti-clockwise. Since it is moment, it will come as it is na kt theta. And anti-clockwise, for anti-clockwise I am using plus. Now moment due to this is force, so moment due to this will be force into perpendicular distance. So this force is kx2, and its perpendicular distance from I center, it is vertical, so horizontal distance from I center, which is 0.4 meter. So moment due to this about I center will be kx2 into 0.4. Now what is the direction of this moment? So this force is like this. You can see about I, it is rotating anti-clockwise, and for anti-clockwise I am using plus sign. Now moment due to reaction at I center about I center will be 0. So we need not to bother about the reaction which is coming at I center. Okay. So this is total summation moment about I center, which is equal to 0. Now put the value. I about I center is 0.833 theta double dot plus the value of C is given. It is 500 Newton second per meter. Now x1 dot, we know x1 dot in terms of theta dot. X1 dot is 0.4 theta dot. So it is 0.4 theta dot into 0.4 plus kt theta, and kt is 1000 theta plus kx2. K is 2000, and we know x2 expression in terms of theta. x2 is 0.5 theta. To into, oh sorry, it is typing error, I think. It is 0.45 meter na. See, distance of perpendicular distance of this force kx2 from I center is 0.5 meter. So moment of this force will be kx2 into 0.5. This is typing error na. So actually it is kx2 into 0.5. So k is 2000 x2 is 0.5 theta into 0.5 equate with 0. So finally it is coming 0.833 theta double dot. Now it is coming in standard form plus, just one second, I am searching for calculator. I am using in mobile. Into 500 into 0.4 into this 0.4. It is coming 80 theta dot plus 1000 theta plus, now this part 2000 into 0.5 theta into 0.5. So it is coming 500 theta equal to 0. Now you can write like this. It is 0.833 theta double dot plus 80 theta dot plus 1000 theta plus 500 theta. So it will be 1500 theta equal to 0. So see, here theta is coming, then here theta dot should come, here theta double dot should come. So it is coming in standard form, and in this standard form we will refer coefficient of theta double dot as ME, coefficient of theta dot as CE, and coefficient of theta as KE. Yes. Now you can calculate anything. Only remember, for general case, whatever formula you have derived, in that formula replace C by CE, K by KE, M by ME, and here ME is 0.833, C is 80, and K is 1500. Okay. So if you want to tell what is the type of damping, calculate zeta, and formula to calculate zeta is CE upon 2 root over KE ME. Okay. Now CE is 80 upon 2 root over KE. KE is 1500 into ME. ME is 0.833. If it is coming less than 1, it will be under damping. Equal to 1 means critical. Greater than 1 means over damping. How much it is coming? You can check the, is it coming 1.132? Calculation is your part, na? Yes, 1.132. It is more than 1 means here type of damping is over damping. Very simple. Over damping means no vibration will occur. Matching with which option? Option C. So for this question, option C is correct. So like this, you can solve the problem of free damped vibration. Na? So we have completed. First, we have discussed its introduction part. Okay. Then we have discussed the general case of free damped vibration. Okay, means we have discussed free damped vibration of general spring mass system. Then we have discussed this free damped vibration for other cases. I think it is clear to everyone. Okay, in upcoming lecture, I will discuss force vibration of single degree of freedom system. Okay, but that's all for today. Today we have tried to cover the free damped vibration. Okay.